Good morning, guys. I hope all is well. Are you ready to rock some physics? Yeah, of course you are. So today, Physics 20, what we're going to do is we are going to look at our vertical dynamics. So last day we focused on our x-axis, and now we're going to be focusing on our y-axis. So when we're looking at vertical dynamics, we're going to be looking at a couple of different forces. Force of gravity, absolutely. And remember how we talked about our normal force last day? We'll be talking about that again today. And we're also going to talk about a cool new force called tension, which is going to be a variant of force applied. So those are things we're going to be looking at today. And another thing I need you to do is I need you to enjoy the meme. Please enjoy. You better be laughing right now. Okay, good. Have to laugh at my jokes, It's important. All right, so we're going to scroll down to our notes here, and we are going to get started. So when we're looking at our vertical dynamics, we're going to be focusing only on forces on the y, and we're going to be looking at objects that are only going to be moving just up and down. So they're not going to have any horizontal forces. So our free body diagrams are going to reflect that. So the two most common don't write on the screen. Use this thingy. Okay, still getting used to the technology here, guys. There we go. So force normal and force of gravity. So your force normal or your normal force is your Fn, and your force of gravity is going to be the force that gravity is going to be applying to that object. Now, the force is going to depend on the mass of the object. So this is the equation from your data sheet. I often just choose to write Fg as equals to mg, but that's okay. That's how it is in your data booklet. And you can find it on your data sheet right here. Okay. See this guy here, right there? G equals Fg over m. That's your equation. Okay. So, once again, as always with force, your Fg, gravity, is going to be in newtons. And as always, mass is in kilograms. So if I give you grams, ladies and gentlemen, convert it into kilograms. Because I promise I will be giving you guys grams and questions. Aiden, no bad jokes. Yeah, you remember your bad grams joke in class. Okay, so our average acceleration due to gravity on Earth is 9.81 meters per second squared. Okay, you guys already know that. You guys already have that number memorized, which is good. And so G is going to be your acceleration due to gravity. So that's your 9.81. You're only ever going to have to use that value as something different is if we're on the planet of, Mars or something, or we're on the moon. And if that's the case, I'll give you G, or you'll have to calculate G, and he'll have all the other info you need. Okay. So this next piece, I want you guys to put a star, and we're going to look at the term weight. Now, in day-to-day language, we tend to use the word weight and mass as meaning the same thing. They're not. Sorry, guys. The force of gravity is another term for weight. So if I ever say the word weight in a calculation, which I will, it really means Fg. Okay, so keep that in mind. That is super important. I would write on test, but we don't have tests. Yeah. You guys did luck out. You guys did actually get to miss writing your kinematics exam. So thank you, COVID-19, for getting you guys out of your unit test, I suppose. Maybe? I'd rather have you be writing tests than be dealing with this diff. Okay. So, where are we? So once again, mass, weight. There is a difference. So bear with me while we scroll down here. Okay. Now, mass is a measure of the amount of matter an object is made out of. So the amount of bits or particles you have is a relationship to your mass. So remember, atoms make us all matter. Yeah, it's a thing. Okay. And weight, ladies and gentlemen, is a reference to gravity acting on that mass. So the larger an object is, the more force it's going to be putting on the ground because of gravity. Okay. So mass, as always, kilograms, and weight, ladies and gentlemen, is newtons. So if you put kilograms beside weight, I will cry inside. Okay, so don't get those units mixed up, please. Mass, ladies and gentlemen, is a scalar quantity because the number of bits you're made out of is not relevant to direction. And weight, ladies and gentlemen, is absolutely a vector quantity, and its direction is always going to be down. Okay, or down. Go. You don't have to write down the value, get it? Write down. You don't have to write the direction down beside weight, because if I say, what is the weight of something? Well, FG is going to be this. Well, FG is always down. Weight is always down. So even though it's a vector, that's the only time you don't really have to write a force, a direction beside your vector, because, well, weight's always down. Okay. All right. So let's look at an example here. So a crane, let's fix that, is used to pick up a car. The car has a mass of 1,263 kilograms. So we're going to write that down. Okay. And the crane operator is slowly lifting it at a rate of 0.0115 meters per second squared. Now look at those units. Is that speed or acceleration? Acceleration is correct. So look at those units. This has that meters per second squared. So that is acceleration. So if you write V, I'll be a little bit sad. Okay. So your acceleration, 0.115 meters per second squared. And now what is the tension in the operator's cable? Now let's think about that word tension for a moment. You need to find my keys. So tension is going to be the force that is going to be applied to this object, in this case my keys, by my lanyard here. Now the force of gravity is pulling my keys down, okay, and the tension is pulling my keys up. Tension is another fancy word for force applied on the vertical, okay, or on a string, okay, or a cable. So your tension, ladies and gentlemen, is equal to a force applied. But in this case, it's by a cable, or it's going to be applied by my keys, or my lanyard on my keys, which is why my keys are neither accelerating up or down, is because the tension on that lanyard, the force applied by that lanyard, which in turn is being applied by me, is preventing those keys from falling, right? Okay, so let's draw our free body diagram. I'm going to scroll this down a bit so it's easier to see. There we go. Okay, so let's draw a free body diagram because that's what we always do. We always draw a beautiful free body diagram. And let's draw it here. Why not? Okay, so what we have is we have FG acting on that car. Okay, and we also are going to be having the tension, or your force applied, acting upwards as that cable is being pulled, right? So this is going to be your force applied, which is equal to your tension. It's supposed to be a T for tension. There we go. So if you want to write force applied as T, that's fine. If you want to write it as FAP, that's fine. Yeah. Show your work, write it down, make it neat. Okay. So I am going to need to do what? What's my next step? Write an Fnet equation. Exactly. So my Fnet is going to equal my force applied, which is my tension, plus my negative Fg. So this is the exact same principle as we did on our previous set of notes, except now we're just building this on the y, and we have no horizontal forces at all to even draw in there. Okay, so let's look at this scenario here. Now we are accelerating. Do we have a force net? Why, yes, we do. Okay. My force net is equal to MA, so I'm going to put that in there. Now, it is equal to my force applied, which is what we're looking for. We're trying to find our tension here, and plus my negative, now let's think about this, FG. Look back at your previous equation. FG is equal to mg, ladies and gentlemen. So I'm just going to substitute in my mg. There we go. I could even rewrite this in a slightly different fashion if you want. Like that. Notice I just converted that plus and negative sign to minus. Same thing. Same thing. So much easier to work with. Okay. Well, now I'm just going to have to rearrange this in order to get my force applied. Well, I'm going to add my mg to this side, which will cancel that out. And then I'm going to add my mg to this side. So MA plus mg is going to equal my force applied. Pretty sweet, eh? Yeah. So now I'm putting my numbers in. Okay, so my mass of 126 and multiply by my 0.115 meters per second squared. That's a 1 there. And then I'm going to add this. First of all, I'm going to scroll up so I don't start writing on my face. There we go. Reselect pen. And I'm then going to add this with my 126 and then multiply that by my gravity, which is 9.81. Now, ladies and gentlemen, be very careful with putting this in your calculators, okay? My advice is to go 126 times the 0.115, hit enter, and then plus bracket 126 times 9.81, bracket, enter. That's what I would do, okay? And then you're going to wind up with your lovely value overall of your 1,253.5.275 newtons. That's our tension. Now, with this long strung out numbers, I'm trying to read it off my notes while writing it down. Not going so well. Let's put this into our appropriate sig digs here. Okay. So when we come back and look at the question, and I can see it on my notes, I can't see it on the screen. You have your 3 sig digs there, and we've got 4 sig digs there. So my lowest number is going to be 3 sig digs, so I'm going to have to put this in scientific notation. So we look 1, 2, 3, 4. Well, that would then round that up to a 4, so that's going to stay there. So we go 1.25 times 10 to the power of 1, 2, 3, 4 newtons. Now, ladies and gentlemen, force is a vector, and unless it is weight, you got to write down your vector direction, which is up. Okay. Here we go. And that, ladies and gentlemen, is a vertical dynamics question. Yay! Vertical dynamics. Vertical dynamics are very uplifting. See what I did there? Yeah. I intended the pun. Fully intended the pun. Always intend the puns. Okay. So, ladies and gentlemen, let's go on to our next question here. Okay, let's erase that line. That line's bothering me. Away it goes. Okay. So a person who is rock climbing and is tethered to a rope, okay, has a weight of 600 newtons. Now, key word, weight. It's not the command I give to my dog when I want her to stay put and not run out the door or run into a door. Well, it is, it doesn't always work. This type of weight is going to be what? FG. Good job. Okay, so weight is FG. That is a key thing, ladies and gentlemen. Don't forget that. So I'm going to write down my FG as 600 newtons. Now, at one point in the person's journey, she slips and falls down slightly, which is a king. I used to do a lot of rock climbing, and yeah, fall. It is definitely a thing. And causes there to be only 485 newtons of tension on the tether. Okay, so I have my tension, which is equal to my force applied, and that is going to be 485 newtons. And what is the acceleration of the rock climber? Okay, so let's have a look-see. Scroll down a bit. Let's draw our free body diagram. So here is the rock climber. Say a much younger Mrs. Bray. And the weight, what direction is the weight? Down. Okay, so the weight is going to be down, which is your FG. And then your tension, that's the rope. That rope is pulling you up when you climb, okay? It's holding you by your harness around your waist. So the tension on that rope is going to be pulling you upwards, okay? That's your tension. We don't have any vertical forces at this point. We're not swinging on a rope. Pendulums are later on in the course, okay? So now we're going to need to make an Fnet equation. Think about it for a sec. Write an Fnet equation. Pause the video, write an Fnet equation. Then come back to this. We're paused, we're waiting. You've written your Fnet equation. Good, compare. Compare what you have. So our Fnet equation is going to equal your force applied or your tension, which is then going to be minus my FG. Notice I just wrote it straight into the easiest form at this point. That's okay. You can do that if you're comfortable with that. Because we know FG is going down, so we know it's going to be in a negative direction, so you can just make it negative if you want. And now, I'm trying to find the acceleration. Well, Fnet is equal to ma. So I replace that ma in there. I already have my force applied, and I have been given the weight. So now I just need to take this expanded equation, and I'm going to divide out my mass to isolate for my acceleration. My mass is going to cancel, and I'm going to wind up with my force applied minus my Fg divided by my mass, and I get my acceleration. So my force applied is 485 newtons minus my 600 newtons. Divide that by my mass. Oops. What's our problem, ladies and gentlemen? We don't have mass. How are we going to find mass? How are we going to solve this problem we've come across? Think about it for a sec. You thinking? Found a solution? Good. So I hope your solution is the same as mine and not a container of salt water. Get it? Solution, salt water, solution. Why are chemists so good at solving problems? Because they have all the solutions. Yeah. Laugh at my jokes, please. So how I'm going to solve for my FG, or my mass, is FG is equal to mg. Well, I always have gravity. And guess what? I have my IFG. So I'm just going to rearrange this to isolate for mass. And then I'm going to cancel. So my FG divided by G is going to equal my mass. So I'm going to have mass is going to equal my 600 newtons. There you go. 600 newtons divided by 9.81 meters per second squared. And that's going to give me my mass. So I'm going to wind up with a mass of 61.16 kilograms. Okay? Sounds good? Okay. So I'm going to bring that number over here, and I am going to put this in here, so 61.16 ... kilograms. Use the entire number in your calculations, ladies and gentlemen. No rounding, whole number. Okay. And we're going to wind up with an acceleration of 1.88. And I'm running out of space. I'm going to scroll up a bit here, guys. There you go. So 1.88 pen 0.025 ... meters per second squared. Now I'm going to need, this is a vector, I'm going to need sig digs negative. It's going to be a negative number. So I have a negative acceleration. I have my lengthy number. I need sig digs. I need units. I need direction. So now because I have a negative acceleration here, what does that mean? Good. It means down. It means that our direction is going to be down. So it is always best to get in the habit of not just leaving that negative in there and actually giving a direction. So it's going to be 1.188 meters per second squared down. Okay. It's going to be our acceleration. Sig digs, units, direction. Box your final answer so I know what you want me to mark as your final answer. All right. Sounds good? Awesome. Okay, so we're going to look at our next piece now here, ladies and gentlemen. We're going to go on to look at what happens when you accelerate on the vertical. Okay. Now, for this, don't erase on the screen, erase on the tablet thingy. There we go. What we're going to do is later on, I'm going to go and hop on the elevator, and we'll sit on the elevator, go up and down a few times, and we'll talk about the forces we're experiencing on the elevator. I'm trying my hardest to keep this interesting for you guys. Bear with me here. Okay, so we're going to do our calculations first, and then I'll make a second video of us discussing forces while I ride up and down on the school elevator. Okay, it's so slow. We're not going to get much acceleration, but it's the best we got. Okay, so when we're going to be accelerating on a vertical in the vertical direction, it's going to result in a change in our weight. Now, the reason why it's going to cause a change in our weight is because our weight is Fg, and Fg is equal to mg. Now, if we're going to be accelerating up or down, we're not just having acceleration of 9.81 anymore. Our weight's going to be changing. Our acceleration is going to be different. So therefore, we're going to have to keep that in mind. If we're accelerating upwards, well, it means we're going to have some weird net acceleration as we're accelerating up and we're accelerating down because of our gravity. So it just depends on what's happening, right? So what level of acceleration, how fast we're going upwards, okay? Now, the change in your weight due to accelerating up or down is going to be what is called our apparent weight. Okay, and what apparent weight is, it's equal to our normal force. So if I ask you to calculate apparent weight, what I really want you to calculate is normal force. So please put a star beside that. I would write on test if we had tests, but it's not on test. So we will write on assignment, I guess. Never ever abbreviate assignment to its first three letters. Yeah, don't do that. Okay, you just did it and you laughed. Yeah, I know you did. Okay, so it is going to be, the reason in this is, once again, as we already mentioned, is we are no longer accelerating at just 9.81 meters per second squared anymore. We're going to be accelerating up, we're going to be accelerating down, okay? And the most common type of question you're going to see with this is going to be elevators. Because when you're on an elevator, you're often accelerating up or accelerating down, okay? So let's work through our example. Okay, I'm going to scroll up. There we go. So if a 75 kilogram person is in an elevator, so I'm going to write down the mass. There we go. What is the apparent weight if the student of the elevator is moving up at a constant velocity? All right, so let's think about this for just a moment. Constant velocity. What does that even mean in terms of forces? Fnet is equal to 0. So ladies and gentlemen, because we said the word Fnet of 0, constant velocity, that's what that means. And we're going to write this down here. So then that way, when it comes to your studying and needing notes for your assignment, it's right there. I wish we still had tests. I know. Not good assessment practice to not have a variety of assessments. Okay. So now we're moving up at a constant velocity. So Fnet is going to be 0. So let's draw our free body diagram. Okay. So we've got our normal force, and we're going to have Fg. I want your arrows, hopefully you were able to draw this one straight. You want your arrows to be about the same size because we're not accelerating, right? We're not going to be accelerating, so you want them to be about the same size, okay? So we are now going to, such a person on the elevator, our motion is going to be going up this way, okay? So let's write our Fnet equation here. So our Fnet is going to equal our normal force minus our Fg. Now, our normal force is going to be our apparent weight, remember that. Now our Fnet is going to equal 0 because we're not accelerating. So because that is 0 newtons, I can cancel that out. So I'm then going to move this over. I'm going to plus my Fg here and Fg over here. So, well, ladies and gentlemen, my Fg is going to equal my normal force. There. Okay, so this is easy. So my Fg is equal to mg, which will equal my normal force. So my Fn is going to equal, so my parent weight, my Fm, is going to be my 75 kilograms, and I am going to multiply that by my 9.81, and that's going to get me my answer of my normal force. So my apparent weight is going to be 735.75. All right, let's get our final answer with right number of sig digs. And when you look at the question, we've got 3 sig digs, so I need to round that up to 736. I need newtons. Now, ladies and gentlemen, remember what we said earlier. For weight, you don't need to write the direction down. The normal force is equal to the apparent weight, so the force, how much you're actually going to be feeling. So in this case, notice that this is the same as just mg. We're not accelerating. So that on the elevator is not accelerating. So therefore, the only acceleration we're experiencing is gravity. So that means when you're moving at a constant velocity, your apparent weight is the same as your weight. Isn't that cool? I think it's pretty cool. All right. Any questions? Sadly, I can't answer that. If you have any questions, email me. Not at my edu email, by the way. My regular GPCSD email. Okay, last question before we go ride the elevator. All right, so let's look at this question here, ladies and gentlemen. We now have a very novel scenario here where we're going to be accelerating downwards now. So we have our rate of acceleration. So let's list that out of our 0.750 meters per second squared. Now, the mass of this individual is still going to be the same. It's still our 75 kilograms. Okay. So let's think very carefully here. Let's draw our free body diagram. Now, this individual is still going to have a normal force. The surface is going to be applying a force to this individual. However, now that we're accelerating downwards, both gravity and our acceleration are going to be acting down. Okay, so our motion is going to be down. So your FG is going to be larger. Okay, so think about when you're on that elevator and the elevator goes down, you feel a little bit lighter for a moment. Because you're accelerating downwards with gravity, you're not putting as much pressure on that floor. So you want this FG to be a little bit lower than the FG that we calculated earlier. So this FN, you want lower than the FG. Okay, so let's think very carefully about what direction we want positive to be. I'm going to choose to make down my positive direction because that's where we're going. We're going down. Okay, because we're going down, I'm going to make down positive. Okay, it's a lot easier if you do it this way, guys. I know some of you guys really like always having down as negative, but trust me on this one, it's going to be so much easier if you make down positive here, okay? All right, so my Fnet, okay, is still MA, still the sum of all my forces, but now my FG is going to be my positive force. It's going down. So my sum of all forces is now going to equal my FG minus my FN, okay? So notice how I put that together now. I made it down. Down is going to be my positive here, okay? So now let's rearrange this guy. My Fnet, or get this guy sorted, my Fnet is MA. Now I have Mg minus Fn. Okay, so ladies and gentlemen, let us solve. Okay, now I'm trying to solve for my Fn here. I'm trying to find my apparent weight. So I got to get rid of that Mg. I'm just going to subtract him out of there. Okay, so now my MA minus Mg is going to equal my negative Fn. Okay, so I am going to wind up with a negative number.
Mr. McPherson, line 1, please.
Lovely announcements. Woohoo! Okay, so I'm going to wind up with a negative number here, and that's okay because that negative number will cancel that out. Okay. So my mass of 75 kilograms, and then my acceleration of 0.75 minus my mg of 75 kilograms multiplied by my 9.81 is going to give me a negative value for Fn, which is okay. Okay. So I'm going to wind up with a number, once you've put this into your calculator correctly, is going to be 679.5 newtons. Now, negative Fn is going to equal a negative answer. Well, that's easy enough. Negative Fn, negative answer. Fn. Now I'm going to put this into sig digs. So I want 3 sig digs. So I want 680 newtons. Now remember, ladies and gentlemen, weight is down, so that means we do not have to write our direction here. Okay. So let's think about this for a moment. Because we're accelerating downwards, that elevator is accelerating down underneath our feet, you're going to feel a lot lighter than you are. So you're putting a lot less pressure on that floor. So our apparent weight is now going to be lower than our actual weight. If you're accelerating upwards, which I'm fairly certain you have in an assignment, lessons at hit, you need to think about this from a different angle. If you're accelerating upwards, that means there is going to be more force on that ground as you're being pushed up. So that means you're going to feel heavier than you are. So when you're making your Fnet diagrams for when you're going up, think very carefully about that and think about how you want to set up your direction. Okay, so ladies and gentlemen, I will create a second video here shortly when I mosey on over to the elevator. I've already borrowed set elevator keys from Miss Penny, and see you in a few. All right, ladies and gentlemen, No batteries or solutions, please.